fire hazard. This is CS155, machine learning and data mining. Hope you're all in the right place. Don't worry, it usually thins out about halfway through the term. All the lectures are also going to be recorded and put on Moodle. So for those of you who don't want to come to lecture every time, although I do encourage you to, I'm obliged to say that, they will be available online afterwards. Okay, so this is machine learning and data mining, CS155. Today it will be pretty straightforward. I'll spend about the first 10 minutes talking about some basic administrative things, and then we'll get into basics of machine learning. Okay, so a little bit about course info. Lectures, since you're all here today, you know this. It's Tuesdays and Thursdays from 2:30 to just before 4 o'clock in this room. We'll also be having a recitation that'll be happening in the evenings from 7:30 p.m. to 9 p.m. in Annenberg 105, again, this room. Usually it only lasts about an hour, a little bit less than an hour. It won't take the full hour and a half. And it'll be scheduled as needed, only scheduled for 6 thus far. The first one, which will be in 2 days in this room this evening, that evening, will be an introduction to Python and using Python for programming machine learning. Okay, so staff, I'm Yi-Sung Yu. I'm an assistant professor in the computer science department here. I teach machine learning. My office is on the 3rd floor of this building, 303 Annenberg. That's where I'll also be having my office hours. We have 4 TAs in the class this year. We have Lucy over here. Ritvik, are you in the room? Okay, so Ritvik. Kevin's here. Where's Kevin? Kevin's right there. And Fabian, is Fabian? Fabian's right there. Okay, so the TAs will be in charge of managing the homework assignments. They'll also be having office hours, and they'll also be managing the discussion forums, which will be where most of you guys ask questions about the homeworks and course topics. Here's the breakdown of the course. There will be 6 homeworks, and it'll be approximately worth 60% of the final grade. I might tweak these numbers a little bit here and there, but this is the rough breakdown. They will be due on Tuesdays via Moodle. The first few will be due every week, and the longer ones will be due every other week. Homework 1 will be released tonight, and it will be due next Tuesday via Moodle. There will be 2 mini projects worth approximately 24–25% of the final grade. The first mini project will be a machine learning prediction competition on Kaggle. And so you guys will be competing against each other to see who builds the most accurate classifier. The second mini project will be a data mining project on visualizing a learned model on a data set. And then there will be a final, which would just be a written exam. Should take about 3 hours during finals week, worth about 15–60% of the final. Any questions on that? Okay. So regarding homework 1, I know that CS156 is formally a prerequisite of this class for undergraduates primarily. And if you have prior experience with CS156, then homework 1 should be fairly straightforward for you. It should not take more than about 3 or 4 hours to do. If you do not have prior experience with CS156, depending on your comfort and familiarity with concepts like linear algebra and calculus, you may find it a bit challenging, so it might take a while, potentially maybe even up to 10 hours. On the other hand, this class is going to be redesigned a little bit this year to be more self-contained, so you don't need all of 156 to take this class. So if you survive homework 1, you've pretty much sort of caught up with what you needed to know for 156 for this class. If you have a lot of trouble with homework 1, I would then highly recommend that you maybe take this class next year after you've taken 156. There's a latest homework submission policy. The policy is you get 48 free hours. So when you submit a homework on Moodle, if you're submitted late, it'll be logged as late, and how late. You get 48 free late hours. Afterwards, you'll be assessed a 50% late penalty for 1 day late, and submissions beyond 1 day late would not be accepted. And you can specify how many late hours you want to use when submitting a homework that's late. So when I taught this class last year, no one actually exhausted the 48 free late hours, so it was never really a problem. Course etiquette. You guys are welcome to ask questions during lecture. If one person has a question, it's very likely that many people here have the same question or a very similar question. So please feel free to ask questions during lecture. However, if the answer becomes very involved, I might defer answering the question to maybe answer it on Piazza or office hours in the interest of time. If you do arrive early or, if you arrive late or need to leave early, that's okay, but please do so very quietly and not be too disruptive of the rest of the class. If you know you're going to leave early, do not sit in the middle of the lecture room, please. And also please adhere to the academic integrity, which is known informally as the 50-foot policy. What that basically means is that you are welcome to collaborate on homeworks and discuss on homeworks and projects. However, the actual homework assignment should be no closer than 50 feet from the other person when you actually write it up. That's the gist of the 50-foot policy. I did not make it up, that's what they call it. Okay, so this is the course website. It's linked to off my website, so if you don't remember this URL, you can just go to my website and you can find it. On the course website, we'll have up-to-date office hours for myself and the 4 TAs. And we'll also have lecture notes, which I'll be putting this lecture note on the website later this evening. Additional reading material if you're interested in reading more details beyond the lecture notes, and the course notes I'll be putting on the website. And also homework. So homework will be released on my website tonight. So regarding Moodle and Piazza, Moodle is an internal Caltech website for those of you who have not used it yet. Here's the link. It's also linked to off the course website. It's used for electronic submissions of homeworks. Solutions will also be posted on Moodle, as will your grades. As will the video recordings of lectures. It does require an enrollment key, and I actually don't know what the enrollment key is. So does anyone know?
It's your last name.
It's my last name. Perfect. Piazza, so Piazza will be used primarily as a discussion forum. So the discussion forum capabilities on Moodle is a little bit primitive, and that was one of the main complaints last year. And so all discussion forums, like questions about homework, questions about certain topics in class, will be done via Piazza. This is also linked to from the course website. Any questions on that? Okay. So on to the meat of the class. So machine learning and data mining. So what is machine learning and data? It's the process of converting data and experience into knowledge. Often actionable knowledge for those of you who want to use it for practical things. So data and experience typically comes in forms of things that all of you probably have some exposure to by this point, are data sets, right? Lots of data. And knowledge is typically in the form of some type of computer model. And the process is typically some type of computer algorithm. And we'll talk about both models and algorithms in this class, and you'll be exposed to some data, although you may have your own that you find interesting. So, people typically talk about machine learning and data mining, and this class will be about both. What is the difference between machine learning and data mining? The two have, they have a very huge overlap. If one were to sort of give a very simple description of the difference between the two, I would say that machine learning focuses more on the algorithms, the technical side. So typically more rigorous. And there's a subfield of machine learning called learning theory that focuses on the analysis of machine learning algorithms and models. Data mining, on the other hand, focuses more on the end product, the knowledge extraction aspect. So typically it uses machine learning algorithms, and the knowledge that you data mine from should somehow be human understandable. So that's what data mining people do. And again, there's a huge overlap because the technical sort of underpinnings are very broad. Machine learning focuses more advanced in the technical underpinnings. Data mining focuses on using that to yield actionable and useful knowledge. So this is the course outline. Today we'll overview some of the basics. A lot of this stuff should be reviewed for people who have taken 156. And then throughout the course we'll be looking at modern techniques in machine learning and data mining that see widespread industry use. Things like lasso and L1 regularized regression, ensemble methods, sequence prediction, embeddings, link factor models, and a little bit on deep learning as well. So that's the end of the course outline. Any questions? Okay, so to introduce you guys to machine learning, I'm going to use a simple example in spam filtering. The goal is to write a program to filter spam. So here are 3 pieces of email. Raise of hands, who thinks the first email on your left is spam? And who thinks it is not spam? Brave soul, brave soul. So I think most of us would agree that it is spam. Second email, who thinks the second email is spam? I know who's not passing this class. Who thinks it's not spam? Okay, good. So the majority thinks it's not spam. Last email. Who thinks this last email is spam? Raise your hand. Okay. And who thinks it's not spam? Okay, that guy should just give me his bank account number because he's not going to need it anytime soon. So it is, most people would agree it's spam. Of course, there's an issue here that I did not, that's sort of hiding under the rug, which is an issue of personalization. Not everyone thinks the same thing as spam, and there are different people with different opinions, but we're going to ignore that for the purposes of this example. Okay, so now, assuming that this is our end goal, to classify this email as spam, this email is not spam, and this email is spam, and to do so in an automated way, let's write a computer program that can do this. Okay, here's in one example, right? In pseudocode, like Python, like pseudocode. A function called spam filtering. Given a document with just the title of the document, here's my spam filtering software. A bunch of if-then else statements. Obviously, this is not a scalable solution because you would have to actually encompass all the possible emails, you would have to write a hugely long set of if-then else statements. Probably one that you can't even sort of enumerate manually. So why is spam filtering hard? Spam filtering is hard because it's easy for humans to recognize if something is spam or not, right? You know it when you see it. But it's hard for humans to explicitly write down a formula or a set of rules describing what you can instinctively or intuitively know is spam or not spam. And even if you could, or even if you tried to, it would end up in lots of ifs, sort of a huge list of if statements. And that tends not to be very robust, right? You can easily get a new piece of email that you know is spam, but is not covering any of your if statements, or not covered well. So this is where machine learning comes to the rescue. How machine learning works, at least the basic version that we'll be talking about for most of this class, is as follows. We assume that there exists a training set, in this particular case of emails that have been annotated as spam or not spam. This is labeled by humans. So in some sense, even though a human cannot write down rules very easily about what is spam or not spam, the human can easily say, oh, I see this email, it's definitely spam, or I see this email, it's definitely not spam, right? So this type of annotation is cheap or easy to get. Given this training set, we're going to build a generic representation of this data. We're going to run a generic learning algorithm. And what this learning algorithm will yield using this representation of this training set is a classification model that then we can use in practice to classify emails as spam or not spam. So I'll talk about first here the most basic representation of data that you can use for text classification, and that is called a bag of words representation. What is a bag of words representation? Well, simply put, it is each document, or email in this case, is represented as a vector of numbers. In the simplest case here, each component in this vector or array corresponds to a word in your dictionary. So in this, for simplicity, here our dictionary has size 6. There's 6 words in our vocabulary. In practice, it could be a million or a billion. Case in point, Twitter, for example, deals with huge vocabularies. People use all sorts of weird abbreviations and hashtags and all sorts of things. So their dictionary of all possible words, quote unquote, is in the order of billions. And for simplicity, the representation would just be binary. 0 if this word does not appear in this document, and 1 if the word does appear in this document. You could obviously imagine more richer representations that are more nuanced, but just for simplicity, this is what we'll use. So this is called a feature vector. 1 feature for each word of vocabulary. In practice, much larger than 6. And for the model class, for the generic model class, we'll first be looking at linear models. What are linear models? Well, they work as follows. So let X denote the bag of words representation for an email. So for example, an array of 6 numbers, or a feature vector of 6 feature values. A linear classifier simply is parameterized by a weight vector and a bias, such that the classifier is the sign of the inner product between the weight vector and the feature vector minus the bias. How does this work numerically? So for those of you who have taken linear algebra, recall that this dot product sort of simply decomposes into an additive sum of the first component of the weight vector times the first component of the feature vector plus the second component of the weight vector times the second component of the feature value all the way to the sixth component minus the values. And if, for any given input x, this sum is positive, then we'll classify the email as spam. And if this sum is negative, we'll classify it as not spam. Or vice versa, depending on how you build your training set. Okay, so let's see it in action. So you have a training set of this form. You have a bag of words data representation of this training set. And the goal is to learn a W and you've decided to use a linear model class. So the goal is to learn a W and a B such that for this example in your training set, you classify it as +1, so the scoring rule is positive. For this example in your training set, you want to learn a WB such that the scoring rule is positive. For this example, you want to learn a WB such that the scoring rule is negative, negative, positive, positive. And the goal is to learn a single W and B that can achieve all of this in your training set. So here's one that does it. If your W is this and your B is this, you can achieve perfect classification accuracy on the first 6 examples in your training set. And we'll talk about how to find these W's and B's in the next lecture in more greater detail. But this is the basic idea. Okay, so congratulations. You now know about probably the workhorse of machine learning. If you go to industry, they'll tell you that the vast majority of their models are in fact linear models, right? They're used in recommender systems, in search engines, things like robotic planning. And by the end of this lecture, you'll understand 75% roughly of the basic concepts of how to build a simple linear model. So, why should this work? Why does machine learning work? Why does a linear model work? Intuitively, at a high level, machine learning works because there are repeated patterns in the data, right? And these patterns, by assumption, at least for now, are encoded in the feature representation. For example, the bag of words representation. So for example, intuitively, there's some relationship or some pattern of relationship between the words Nigerian prince and how that appears is representing your features as being indicative of spam, right? It's a systematic pattern. Machine learning is the process of finding those systematic patterns in the data. So if you're decided to find patterns that take the form of linear models over features, then you'll learn that you should have a high weight on words for Nigerian prince as these correspond to in your feature representation in order to learn a classifier that is predictive of spam. There are 2 basic machine learning problems. The first is classification. And in classification, the idea is to predict which class an example belongs to. So in the spam filtering example, there are 2 classes, spam and not spam. So, and so the classification is binary. And so there's a positive class and a negative class, and so the linear model takes the form of this. The second setting in machine learning is called regression. In regression, the goal is not to predict a discrete class, but a continuous value, typically corresponding to some real value thing you're trying to predict, or a probability in some cases. For example, maybe you don't want to just learn a classifier that classifies something as spam or not spam. You also want a confidence rate. I want my model to predict not only that it thinks it's spam, but it thinks so with 80% confidence, right? Because if it thinks so with 80% confidence, that's quite different in many applications as if it thinks so with 50% confidence, right? Imagine, you have some risk-sensitive scenario like cancer detection, right? You want a model that looks at X-ray images and automatically detects if there's cancer or not. You want to be, 99% sure that there's no cancer. before you sort of automatically sort of assess that there's no risk and don't show it to a medical professional, right? So in many cases, being able to predict the probability or confidence of a prediction is just as important as predicting the label, because the cost of a misclassification could be very high in those settings. And so in those cases, we want to do regression. And for regression in a linear model, you simply just remove the sign in the simplest case. There are sort of more complicated scenarios, but for now, we'll just look at this setting. And the two, of course, highly interrelated. So for example, you could train using a regression, and then you could use it for classification. For example, I could have a regression model that predicts a bunch of numbers, and then I slap a sign onto it, right? So they're actually very highly interrelated, and we'll see some of their relationships as the course progresses. Okay. So here's a regression problem. So if I take this same weight vector, same model as before, and I remove the sign, then I get this. Right? It's perfect classification accuracy, right? Because if you take the sign, the sign corresponds to the annotated labels in the training set. But now you can actually look at the numbers, right? It's really confident that the model is really confident that this email is spam because of this combination of features. It's really confident that this email is not spam because of this combination of features, and so on and so forth. And this is assuming a bias of 1.5. If you shift the bias up or down, then your threshold for thinking something is spam goes up. If you shift the bias up, your threshold for classifying something as spam goes up. If you shift the bias down, your threshold for classifying something as bias goes down. So classifying something as spam goes down. Okay, so a little bit of formal definitions. So I'm going to call a training set as a set of x, y pairs. So x is your input features, y is your label, let's say. So the input features are just a vector of d numbers. And for binary classification, the labels is either -1 or +1 or 0 or 1 or something equivalent. Then there's something called a model class, or also known as a hypothesis class. And so for linear models, the hypothesis class is all W and B such that the scoring row looks like this. That's called a hypothesis class. And the goal, given a training set and a hypothesis class, is to find a parameterization within your hypothesis class that predicts well on your training set. And so what remains in this formal definition is how to quantify, how to formalize well. Right? This is the remaining fuzzy part. So the typical way to quantify how well something, a model is doing on your training set, is to quantify it via what's known as a loss function. So here's one example of a loss function called squared loss. And squared loss basically says, if the true label is A, and my model predicts B, then the loss I incur is the squared difference between A and B. Right? And so given a loss function, the learning objective, the goal of the machine learning algorithm, is to find a W and B that minimizes the loss on the training set. And this is what's known as an optimization problem, because the minimizer of this thing is the optimal solution. So there are many different loss functions that one can consider. Squared loss is just one. So here's a couple of examples that are beyond squared loss. For classification, the loss function in some sense, or the default loss function that you care about is called 0-1 loss. And that's basically, if the true answer is A in the training set and my model predicts B, then the loss is 1 if A and B are not equal, and the loss is 0 if A and B are equal. So for those of you who haven't seen, this is called an indicator function that takes values either 0 or 1. And it takes values of 1 if the clause is true, and it takes value of 0 if the clause is not true. So the loss is 1 if A does not equal B, and the loss is 0 if A equals B. Sometimes A and B are expressed as sort of real values, not as just a class, in which case for binary classifications, so these two are equivalent. It's equivalent to say that in 0, 1 loss, that the loss is 1 if the sign of A is not equal to the sign of B, and the loss is 0 if the sign of A equals the sign of B. For regression, by far the most common loss function people use is squared loss. So here, A and B are real values. You're trying to predict the actual real value numbers of A. If A is 0.3, then you want to predict 0.3 as close to 0.3 as possible. And so this is the loss you suffer as you deviate from that prediction. And so how you sort of use this in practice, of course, is that A is your label and B is your prediction. So here's the relationship between 0, 1 loss and squared loss. So on the x-axis, we have the score of the function. So remember, this is the linear model score for some input x. Right? And the y-axis is the loss. So for 0, 1 loss, as soon as the threshold, as soon as the function score passes the positive negative threshold, 0, it goes immediately from 0 to 1, or vice versa, depending on what the true label is. Here the true label is 1, is the positive class. So as soon as the score of the linear model becomes non-negative, becomes positive, the loss jumps from 1 to 0. Squared loss, on the other hand, looks like this, right? It's just the quadratic curve centered at 1. One thing to keep in mind is that since you're finding the minimizer of this loss, the scale, the vertical scale, does not matter. All that you want is the shape, right? You want to find the shape. What the shape means is, as you deviate for squared loss, as you deviate from the perfect prediction, the loss grows quadratically, right? I can multiply that by 5. I can multiply by 10. It doesn't matter. The optimal solution is still here, and your penalty for misprediction grows quadratically. For 0, 1 loss, any prediction here gives you 0 loss, and as soon as you cross the 0 threshold, you incur some non-zero loss. And if you scale this from 1 to something else, it doesn't really matter. Note also that if your model happens to get 0 squared loss, it also implies perfect 0, 1 loss. Squared loss is known as a upper bound on 0, 1 loss. So if you get perfect squared loss, you also get perfect 0, 1 loss. But not vice versa. The converse is not true. So, this is the model that I solved using linear regression, minimizing squared loss on this training set of 6 examples. Spam is the positive class, not spam is the negative class. These are the feature representations. With this model, I can get perfect squared loss, 0 squared loss. I exactly predict positive +1 for this example, exactly predict +1 for this example, -1, -1. There's no sign here. This is the actual real value that the linear model is predicting.
Is there a unique solution?
Not necessarily. In this particular case, it's not unique because there are 7 parameters and 6 constraints. Are you familiar with?
Yeah.
Okay, so if you're familiar with sort of optimization in linear algebra, you know that solving this is a system of linear equations with reduces to having 7 free parameters with 6 constraints, effectively, which means that there's an infinite subspace of solutions that achieve 0 squared loss in this particular example. In practice, the number of features and the number of parameters is usually less than the number of features because you want a compact representation of the data.
Then how do you choose which solution to use?
In those cases, typically there's a unique solution.
Okay.
Yeah. And this will become more evident later on in the course. Okay, so most of machine learning boils down to this formula, right? We define some loss function, we define some model class parameterized by some parameters, and given a training set of xy pairs, we want to find the parameterization of our model class that minimizes the loss function. This is what the vast majority of machine learning boils down to. So typically this requires an optimization algorithm. The simplest one is called gradient descent. If you've taken multivariable calculus, this should look not too foreign to you. So you start with some initial point of your, you start with some initial point, W and B, and at each iteration, you update your point in the parameter space by walking along the gradient or the derivative of this function. Right? So you take the partial derivative of this function with respect to W, you take the partial derivative of this function with respect to B, and you do a minus because you're doing minimization, not maximization, and then you make an update. And you just continue this process until you've converged to the optimal solution.
So is it local, global?
I'm sorry?
Is it local, global?
So if the loss function is convex, which I'll talk about later in the course as well, then this converges to a global optimal. If the loss function is not convex, then it will converge to a local optimal. There are cases where it may diverge, but we'll talk about that actually on Thursday. But so all those details about convergence and local global we'll talk about on Thursday. This is just sort of a high-level picture. And then you loop for some large number of iterations until you think you've converged, and then this is the model you return as the minimizer of this optimization problem. Just a little bit of review over gradients. So if you want to compute this gradient by linearity of differentiation, you can move the partial derivative inside the summation. If the loss function is squared loss, you can apply chain rule, which is basically just you differentiate this and then you move the partial derivative inside the loss function to the term that depends on set W, which is this guy. And then because this is the form of F, the partial derivative of this with respect to W is simply just X. So this is the actual gradient of this guy for squared loss and linear models. Just a couple steps of multivariable calculus. And I'll talk about more details of this in the next lecture. How to get it to work, what are some tricks to get this to work in practice, which will be on the homework. Okay, so in order to solve this optimization problem, we're going to take gradients. That's what most of machine learning is about. For square loss, it's pretty easy because I just showed you the derivative. What about for 0, 1 loss? How do you do gradient descent for 0, 1 loss? Anyone want to take a crack at it?
Can you use a smooth approximation to 0, 1?
You're jumping a couple steps ahead. Okay, so as Galton pointed out implicitly, 0, 1 loss is not smooth. In particular, it's not even not smooth. It's discontinuous, right? So how do you compute the gradient of 0, 1 loss? The gradient here is 0. So you don't. If you're here, right, you want to get to here, but the gradient, the slope of this curve, is flat. So you don't know if you should be going this way or this way because you don't have a global view of this curve. For squared loss, for example, the slope points down this way. If you go this way, the slope points down if you go this way. So if you're here, you take a step this way. If you're here, you take a step this way until you converge to this point. For 0, 1 loss, if you're here, you have no idea how to get to here. If you're here, you don't know how to move anywhere. And if you're here, it's actually discontinuous because so the gradient is undefined. So the gradient is either 0 or undefined everywhere. So 0, 1 loss is flat or discontinuous everywhere. So the gradient is 0 or undefined everywhere. So this is a very difficult function to optimize. And 0, 1